So here again, the simulation of the road sign, this traversal of scales, which we could now characterize in terms of an energy cascade going from large scales to small scales. And specifically in this picture, I was focusing on elements that neighbor the boundary, where we have this boundary layer around here. And if we zoom into this boundary layer, then I have here certain graphs, and these graphs, they say something about the predictable statistical behavior of the flow in the boundary layer. And that's what we're going to talk about in this video. So again, one of those beautiful pictures from an album of fluid motion, and where I'm zooming into the boundary layer of, I suppose this is not really a sphere anymore, but some curved surface. And well, we've talked about boundary conditions before, and also boundary layers for the advection diffusion equation, where we know that we get this incredibly steep behavior of our solution. And that is precisely what's happening also for the Navier-Stokes equation. As the Reynolds number goes up and up, you get a more and more steep solution neighboring the boundary. And there's quite a bit to tell about the turbulent boundary layers, because they're slightly different from laminar boundary layers. And we can really only talk about them from a statistical perspective, because what's going to happen is that in laminar flow we have these nice layers, and you would get a relatively stable solution field. But as turbulence starts to develop, we get this mixing of fluid motion, meaning that fluid on the outside, which is at a higher velocity than what is on the inside, where our boundary condition is a no-slip flow, a zero flow, so that starts to mix, which means that if we zoom into that boundary layer, then for a laminar flow you might get a curve like this. If we then get turbulent flow, then the high velocities start to mix in with the boundary layer, and you would get a much steeper mean solution field. That is also going to fluctuate. Maybe you get solution fields that are at certain times have a much smoother boundary layer, but in other cases it might have an extremely steep boundary layer. And all we can really talk about is the mean behavior. And it turns out that actually we can get pretty good characteristics of these mean flow behaviors in the boundary layers, and those are what we call the laws of the wall. And there's two laws of the wall at two different regions away from the boundary, and what they are really very straightforward equations that's going to predict the mean behavior of the flow at these distances from the no-slip boundary condition. So in order to obtain these relations, we have to introduce certain normalizations, as the one we're seeing on the left here. Now again, I don't want to go into too much detail here, but the thing to realize is that you get an incredibly steep characteristic mean of the flow. And this is so steep that let me first address this graph a little bit better. As what we're seeing here is the mean flow normalized in terms of the distance with respect to the wall. So this is the steepness of our boundary layer, which is subdivided into three distances. The viscous sublayer, which is directly neighboring the wall, that's where it's incredibly steep. Then a little bit further away we have the log-law region, where we have a linear relation in terms of log-log, so an exponential relation. And we have a transitional region, and that's called the buffer layer. And only past this log-law region would you get certain mean flow statistics that are away from the object, right? So this is all very close by the object. So it is almost impossible to refine to the level of this boundary to get a good representation of this boundary layer. In order to get finite element approximations of this, you would have to refine to a point that it's just computationally unfeasible. But at the same time, the behavior at this boundary is incredibly important because this is precisely what trips turbulence. Turbulence has to be tripped. In a perfect scenario where you have an extremely high Reynolds number flow, but you have a perfect initial condition, you would still get a smooth solution. And well, the chaotic nature of turbulence means that if we only perturb that smooth solution just by a little bit, then suddenly you're going to get this chaotic behavior, or this chaotic response, this unstable response. And that is precisely what boundary layers tend to do. They trip turbulence, they produce instabilities. And if I actually show the simulation here, you see that that's precisely what's happening at the bottom. You see these streaks of vorticity that are being produced at the boundary. So the boundary is producing this turbulent flow. It's tripping the turbulence. So boundary layers are incredibly difficult to take into account because they occur at such small length scales, but at the same time they're also very important. So there's I think there's 3 different approaches that I would like to address when we talk about this. The first one is very obvious, very straightforward refinement of your mesh towards the boundary layer, and that is called a boundary layer mesh. Now, you would typically not quite do that as what we're showing right here. We use tetrahedral elements. In order to use tetrahedral elements, we have to sort of homogeneously refine towards the boundary adaptively. But you could probably do this better by orthotropically refining, meaning that along the boundary you keep your length scale fixed, and only in the direction of the boundary layer do you start to refine. So then you get a very thin element that are very stretched. Typically, high aspect ratio elements are bad, but because we know that the true solution conforms to that aspect ratio, that's actually not a problem at all for these cases. So that would be the most straightforward strategy for handling a case like this. Now, that's going to be very tricky because you would have to refine incredibly far, especially as the Reynolds number goes up. So that's typically also not feasible. You would still do this if you don't have an alternative, because it's better than not doing anything. Again, taking into account the boundary layer properly is highly important also for the far field behavior of your flow, because the boundary trips the turbulence and produces the mean, root mean square characteristics of the flow. So you would at the very least do this, but you can do better. And there's, I think, 2 interesting ways of doing this better. One that is very difficult, but I think is actually the most elegant way of handling this. And that is by using this known behavior of your flow. You know that the flow is going to have this mean characteristic. So you could actually use these equations, this log law equation, as a shape function in the element neighboring the boundary. So for our shape functions, our basis functions, we typically always use linear equations or quadratic equations or cubic equations, polynomial equations. And the reason that we do this is that we can work out the integrals in our stiffness and our mass matrices relatively efficiently with quadrature rules. But there's no fundamental reason for why we would need to use these types of functions. You could use arbitrary functions, you could use sines and cosines. And now we have certain properties that we want from these functions. We want them to be localized because we don't want to have to integrate the complete domain for every new basis function. That would be impossibly expensive. So you want to have a localized function as a basis function, and you want to have a function that is conforming to the Sobolev space from the weak formulation, right? So typically we use an H1 Sobolev space. So you want to make sure that your basis functions are functions in H1, which typically just means that they have to be continuous. And discontinuous Galerkin methods were an opposite to that, for which we had to introduce all kinds of tricks to handle that. So those are, but other than that, there's really not much requirements for your basis functions. I mean, those are just two things that we want. We don't even need them, right? You could use global integration, you could use discontinuous Galerkin methods, but nevertheless, that's what you want. And certainly the polynomial basis functions are no, there's no law that says that you have to do this. So what you could do is you could use basis functions that look precisely like these functions, because you know that that's what your flow is going to look like. And using these functions, you might actually get incredibly good representation of the boundary layer, because again, you know that the boundary layer is going to look like this. So that is, I think, the most elegant way of handling this. It's also very difficult because, well, you have to really, this is a very intrusive method in the sense that you really have to go very deep into the finite element code to change things to make this work, right? You have to get precisely the elements surrounding the boundary layer. Then you have to add basis functions on top of that. These basis functions are going to look quite complex. Then you have to introduce new integration rules for those elements. So it's a very elegant solution, but also very difficult. The second solution that is much less intrusive, albeit still a little bit intrusive, is to actually borrow from discontinuous Galerkin methods. We know that discontinuous Galerkin methods, one of their strengths was that, well, they could treat discontinuities. If you have certain sharp layers, then it makes sense to kind of release the idea of continuity and say, well, we're going to use functions that are able to capture those discontinuities by discontinuous basis functions. And in a sense, a boundary layer is precisely that. It is an incredibly steep layer. And trying to take that into account with a continuous basis might simply not be your best bet. And that is where the idea of weak imposition of boundary conditions comes from. And that is what I want to show with this final slide here. I have here two simulations of the same problem. One where I'm using strongly enforced no-slip boundary conditions and one where I'm using weakly enforced no-slip boundary conditions. Okay, let me take one step back. What am I computing here? This is a box inside of a periodic domain of flow moving between two plates. So you can think of this as two infinitely wide, infinitely deep plates parallel to one another, where we have flow moving from the left to the right that is driven by a pressure differential. Now that's a very classical benchmark problem for turbulent computations, because those are cases where we can simply take out one piece of our domain, we have periodic boundary conditions all across, and then we can get very interesting statistics of the turbulence for different Reynolds numbers. So that's what this is. We're taking a certain box outside of this infinitely stretched plate and using periodic boundary conditions across these sides and across these sides. Now at the top and the bottom we have known boundary conditions. We have a zero flow, we have no slip. So that's causing boundary layers on the top and the bottom. So the flow is moving from the left to the right, but it's being stopped at the top and the bottom. So if we use a typical finite element method where we're simply going to prescribe the values on the top and the bottom, and then we get the solution that we're seeing on the left. But we can do something else. We can borrow from discontinuous Galerkin methods. We're going to say, well, I'm not going to set the values on the top and the bottom directly to zero, but rather I'm going to allow for flexibility, and I'm going to introduce numerical fluxes that are consistent, conservative, and in a mean sense make it satisfy the no slip conditions. And by allowing that flexibility, we see already that we get a completely different solution field. So now obviously the question is, what is the correct solution field? Well, in order to understand that, we have to look at the graphs in the bottom. These are obtained from a direct numerical simulation. So a simulation that heavily refines, takes into account all the skills of the physics, refines the boundary layer up until the log law, the buffer law, etc. And then you get these characteristics of the flow. We have a mean velocity and root mean squares in x and y. So those are what we refer to as the true solutions. Those are the graphs that we want to get. The black lines is what we want to obtain. Let me rerun the simulation. What we see is happening is that for the strongly enforced, the flow speeds up more and more and more, and it doesn't really arrest. So what we see if we add that line on top of, well, the graphs on the bottom here, then we see that we get a huge overprediction of the mean velocity flow inside of our channel. There's an overprediction by almost 50%, and I don't know that this was already a steady configuration, so maybe if you run for longer, you would get an even larger overprediction. And also the root mean squares of our velocities are completely off. So this is showing that the strongly enforced boundary condition is not doing what we want it to do. So the idea then to use a DG type method to weakly enforce the boundary conditions, well, what does that bring? Then we get the blue lines here, and we get a remarkable improvement of solution right here. And this is on a very coarse mesh. So we get a very good approximation to the mean and to the root mean squares. Now I'm going into this in the next video a bit more into detail. We'll try to understand why this is happening, why the weak enforcement is fixing that, and then we're going to derive the equations that you would need for this weak enforcement coming from a DG perspective. Yeah, but that's it for now. Mostly on this video I wanted to focus on the physical behavior of the flow in terms of well, the boundary layers, the local. Okay, so far we had 3 videos on the physics to kind of get an understanding of what turbulence is, and from now on we're going to go back into the numerical methods and going to try to develop methods that take into account this physics to produce stable methods that are able to predict the solutions accurately. Okay, thank you for your attention.